Hi, we wanted to present our project to you, which we've been working on this summer through Climate Plus at Duke University. We're creating a generalizable model for urban heat islands in the United States. My name is Ella, and I'm a rising senior majoring in environmental sciences.
My name is Yaslin, and I'm a rising junior computer science major at the University of Maryland, Baltimore County.
My name is Ritik Borua, and I'm a rising senior studying computer science at Duke University.
And my name is Umayma Barada. I'm studying data science as a rising senior at Duke University.
Before we dive into the details of our project, let's take a moment to talk about what urban heat islands actually are. Urban heat islands are areas within cities that are significantly hotter than nearby rural regions. This temperature difference is caused by urban structures like asphalt, concrete, and buildings that absorb and retain heat. This might not seem like a big deal at first, but it actually has serious consequences. Higher temperatures in cities lead to more electricity used, can increase health risks, especially during heat waves, and can strain infrastructure that's not built to handle the extra demand. That's why understanding and predicting urban heat islands are so important, especially as cities continue to grow and climate change intensifies these effects. Most urban heat island models are developed for specific cities, but the goal of our project was to build a generalizable model that could predict urban heat even in regions with limited or no data. To make that possible, we focused on three main data sources. First, we used the ERA5 land data, which provides high-resolution meteorological data with a wide range of climate variables. We selected specific ERA5 features like solar radiation, dew point, wind speed, and surface pressure because prior research has shown that these variables have some of the strongest impacts on overall temperature. Second, we incorporated the NOAA traversal data, which was collected from the Kappa Heat Watch campaign. In this campaign, volunteers drove along predetermined routes around the city with temperature sensors mounted to their cars. This generated thousands of temperature readings, which are used to create detailed heat maps showing how temperatures vary across the city throughout the day. Finally, we used the local climate zones and NDVI datasets. LCZ provides a standardized way to classify land types, including forests, dense tree covers, and urban structures, while NDVI complements this by capturing more detailed vegetation health and density data. ERA5, LCZ, and NDVI are all available globally, making them ideal for future initiatives of building a model that can generalize to any location in the world. By aligning all these sources, we were able to build a multi-city dataset that helps us test how well our models could predict urban heat in different cities. Our final dataset included data from 42 U.S. cities with temperature readings collected during the morning, afternoon, and evening time slots.
We started by aligning the data because our sources came in different formats and resolutions. We converted them all into 100-meter resolution rasters chosen specifically to match the land use data. Next, we wanted to capture the general climate conditions in each city for the exact day of the NOAA temperature readings. To do that, we averaged the ERA5 land variables over the full day for each city. Since our goal is to understand how urban structure contributes to heating, we needed a way to isolate that effect in the NOAA data. For each city and time slot, say Raleigh-Durham in the morning, we computed the 5th percentile of NOAA readings and averaged them. This gave us a proxy for the temperature in a hypothetical empty land scenario. Then, for each observation, we subtracted this 5th percentile average to get the temperature anomaly, which isolates the added heat from the built environment. We also wanted to capture the urban surroundings of each data point, so for each point, we mapped the coordinates to land use data, took a 500-meter buffer around it, and averaged the land use composition within that buffer. This let us go beyond the exact location and include the neighborhood effect on temperature. Since the land use variables are compositional because they sum to 1, we had to deal with the simplex constraint. To make them suitable for modeling, we applied a log ratio transform. Then, since we had 17 land use classes, we followed up with principal component analysis to reduce dimensionality. Once all pre-processing was done, we had a multi-city dataset per slot across 42 US cities. Our features included the transformed land use variables and the averaged ERA 5 land climate variables. Our target was the temperature anomaly computed from the difference with the 5th percentile average. To train the models, we used data from 32 cities. The remaining 10 were held out as the test set. We evaluated model performance using Pearson's R. We worked on two models, a mixed effects model and a linear regression with interactions. I'll now walk you through the mixed effects model first. Before diving into our specific model, here's a quick overview of what a mixed effects model is. At its core, it's a linear regression, but it's particularly useful when the data is grouped. For example, we could imagine a grouping by shared climate, say Boston, Seattle, and Asheville in one group, and Atlanta, Austin, and Arlington in another. The goal is to capture both global trend across all cities and local differences within each group. A mixed effects model does this by using fixed effects, which estimate coefficients that are shared across all groups, and random effects, which allow certain coefficients to vary by group. This structure allows the model to generalize better and adapt to differences between cities. Now, looking into our inputs. First, from the PCA of land use composition, we had 16 principal components. To reduce complexity, we selected the top 5 principal components, chosen because they together explained over 70% of the variance in the land cover data. You can see from the graph here that the cumulative variance reaches 70% at the 5th principal component. Second, the model benefits from the group data. Since we didn't have pre-existing city groups, we created our own clusters that reflect both climate and urban structure. We used k-means clustering applying to ERA 5 land climate variables, NDVI for vegetation, and building type distributions. Here's how the clustering looked like after PCA projection. You can see a moderate separation. We also tried UMAP for better cluster interpretability. The final result gave us 4 clusters, 2 large and 2 smaller ones, which grouped cities with similar climates and urban structures. Using these inputs, here's how we set up the mixed effects model. For the fixed effects, we had an overall intercept representing the baseline temperature anomaly. The top 5 land use principal components with coefficients shared across all cities. So the fixed effects part estimated a global average contribution of land use to urban heating. As for the random effects, each cluster had its own intercept, adjusting the baseline temperature anomaly. And each cluster also had its own coefficients for the 5 principal components we can see here, to adapt how land use influences temperature within that cluster. In other words, for each observation, the model adjusted both the intercept and the land use effects based on the cluster the city belonged to. This is the full formula that we got, and it's the predicted anomaly for observation I in city J. The results were promising. While not perfect, the model produced positive and interpretable results, showing that this method can uncover useful insights about urban heat contributions. Interestingly, the AM time slots performed best, possibly due to more stable early day temperature conditions.
When it comes to the linear model with interactions, this is predicting temperature anomalies using raw land use variables at 100-meter resolution. This differs from the mixed effects model, which is using the buffer at 500 meters. Within this linear model are interactions between the ERA 5 and land cover variables, so essentially meteorological and land cover variables. A ridge regression was also applied to prevent overfitting of the model. Below we can see the results. The main ones we would like to highlight are for the morning, the linear regression with interaction seems to perform very well in comparison to the rest of the models. Looking more deeply at the interaction terms for ERA5 and land cover variables, we wanted to highlight the most important features from the linear regression model in the morning. Looking at this table, we can see that average wind speed is leading to decreased temperatures in a city. We're also seeing that compact low-rise buildings have increased temperatures, and open low-rise buildings have decreased temperatures. Finally, we're seeing that average dew point, which is a proxy for humidity, specifically when paired with compact mid-rise buildings, is leading to decreased temperatures. We believe these are important to highlight when it comes to adding more nuance into our model and really understanding how climate affects land cover and heating.
On this slide, we are looking at the practical output of our model and discussing its future implications. The two images show a case study of Harrisonburg, Virginia, where was a hilltop city, meaning the model was trained without any data from this location. On the left, you'll see our model's prediction of morning temperature anomalies. The darker red areas pinpoint hotspots where the temperature is predicted to be significantly higher than in the surrounding rural areas. This is the urban heat island effect visualized. On the right is the actual land use map of Harrisonburg. The orange and red areas represent dense urban structures like compact mid-rise and compact low-rise buildings. The key takeaway here is the strong qualitative relationship you can see just by looking at them. The predicted hotspots on the left map almost perfectly onto the dense urban core on the right. This demonstrates that our model successfully learned the underlying connection between urban structure and temperature. This is critically important for future work because it means we can now use this model to test mitigation strategies. By modifying the land use inputs, we can simulate how interventions like adding parks or changing buildings density could effectively reduce these urban hotspots and create cooler cities. To make our findings more accessible and actionable, we created the Urban Temperature Predictor, as you see on the canvas. It's an interactive dashboard that lets anyone use a simplified version of our model. You can adjust sliders for different factors from land cover types, like compact high-rise, to meteorological combinations like wind speed, and instantly see the predicted impact on urban temperature. This turns our research into a practical planning tool, allowing urban designers and policymakers to explore different development scenarios and make data-driven decisions to mitigate urban heat. Thank you for listening to our presentation. If you have any questions, please reach out to us.